So, good afternoon, everybody. So let's start the afternoon session. The speaker is Augusto de Leles Araújo, and he's going to talk about twisted homo and hetero bilayers, a high-throughput DFT database. It's all yours.
Hello, good afternoon, everyone. My name is Augusto de Leles Araújo. I am a postdoctor under Adalberto Fazio here at Ilum. And today I will briefly talk about a work we are finalizing entitled Twisted Homo and Hetero Bilayers, a High-Throughput DFT Database. This name suggests this work is about building a database for bilayers with distinct twist angles. In this work, also involved are Pedro Sofia, the PhD student of Professor Fazio, and Professor Felipe Castro here at Ilum also. Before getting into the work itself, I will provide a brief context. First, the first two-dimensional material obtained was graphene, a zero-gap semi-metal discovered in 2004. Its discovery boosted the study of this new class of materials, 2D materials, which quickly expanded to include metals, semiconductors, and insulators, both trivial and topological materials. Now, two-dimensional materials cover a wide range of properties, often distinct of their 3D counterparts. In addition to monolayers, the study of the stacking of layers, like bilayers, has also shown advantages in material engineering, especially for systems with van der Waals interlayer interactions, which provide interlayer coupling, but without forming covalent bonds. This strategy allows to combine of properties of each material or of each layer in order to modulate, optimize, and even induce new properties for specific applications, enable so efficient material design. As an example, I will cite a recent work published for our group. Here, we achieved the control of the spin degree of freedom in a topological insulator through a van der Waals interface with a 2D ferromagnetic insulator. Here, by tuning the number of the topological insulator layers and the magnetization direction, we observed distinct spin detectors behaviors across the Bryon zone, that is distinct electronic landscapes of the topological states. Returning to context, more recently, a new degree of freedom has been introduced in material engineering relation, rotation between layers in stackings, which give rise to twistronics. So, in twistronics, the rotation allowing interlayer coupling modulated. However, combine this degree of freedoms of the system, that is, combining different materials in stack with different twist angles, creates a wide configuration space to explore, which represents a significant computational challenge. To overcome this challenge, in this work, we developed the Samba code. The Samba code is a Python workflow capable of generating and calculation structural and electronic properties of the twisted bilayers. In a high throughput approach, using the calculations for VASP DFT package. Using the Samba code, we are building a robust database, having already generate over 18,000 distinct bilayer structures with first principle calculations performed on around 1,000 of them structures, and this number continues to grow. The main goal of this work is to provide both theoretical and experimental guidance to accelerate of the discovery of the new 2D materials for specific and tunable properties through twisted engineering. So our workflow college Samba has many three functionalities. First, generating bilayers for distinct twist angles. Second, perform high throughput DFT calculations. And third, analyze and extract relevant information to populate the database. As a point start, this work, we selected the materials for bilayer construction. These were exfoliable natural materials or synthesizable materials previously reported in the literature, and with predominant van der Waals interaction coupling. This gave us a list of 63 materials, mainly from the graphene family, or 2D chalcogenides, like TMDs. While 63 materials may seem small, the pairwise combination of these 63 monolayers result in 2,060 different materials combination, materials pairings, and an even greater number of the distinct structure when distinct twist angles are considered. So, with monolayers structure files in hand, you use the Samba code to generate how possible bilayer configurations. Essentially, this code scans how possible linear combination of the lattice vector for each material, that is, how possible cells, unit or supercells for each material. Each cell for material A is compared with all cells of material B. A match is identified when both cells are sufficiently similar. The similarity is defined by maximal deviation, maximal percentage deviation. So in this work, we set less than 3% for area or and lattice vector modules for each cells, and less than 2% limited to 2 degrees for open angle of this lattice vector for each cell, which the criteria are meet the two materials, the two cells are merged into common intermediate cell to minimize the lattice mismatch between materials. This brute force approach used in the Samba code often returns hundreds to thousands structures for the same material combination. And finally, when these distinct twist angles naturally emerges. Finally, these structures is compared and identical structure is filtered out, keeping only unique configurations in the database. In this work, we limited to final bilayer structures to maximum of 100 atoms per cell, resulting in over 18,000 distinct bilayers in the database. It is important to highlight that the current database focuses on the analysis of homobilayer. It is important to highlight that the current database, like the EDB, focus on the analysis of homobilayers or heterobilayers formed by single unit cells per layer. And in your database, this subset represents less than 5% of the total. So instead on focus on the many different materials combinations, we chose to analyze fewer combinations of materials, but with many distinct twist angles, capturing a wide configuration space, then whose other side will be completely lost. So, with bilayers structure files in hand, we use the Samba high throughput module to generate necessary input files for different VASP calculations. These include optimal structure optimization and electronic calculations. I will be illustrated better these processes in the next slides using on bilayer example. So after the DFT runs, the code the VASP output files are parsed for relevant information about structural configuration and electronic calculations, and results are stored in the database. So to better illustrate these processes, I will take the bilayer between graphene and Jacutin gate as an example. Jacutin gate is a topological insulator discovered in Minas Gerais in 2008. Here we have four distinct bilayer configurations, differing each other by number of the atoms in the cell, rotation between layers, and lattice mismatch. Taking the bilayer configuration with smallest mismatch, highlighted in red, the first workflow step is the structural optimization. Here, which the interlayer separation, the optimal interlayer separation and binding energy are obtained. Then the energy as a function of the lateral displacement of the top layer is computed, and alignment favorable and slide energy are obtained, and finally the structure is completed and relaxed. After structure optimization, the Samba code provide the electronic calculations, where the band plots, projection of spin components, projection of atomic layer are obtained. Here we can see in this example that the conjugate of graphene in blue is preserved, and Jacutin gate's gap remains true, but with a spin split. In addition, the Samba code provide the density of states, those orbital projections, and analysis of electrostatic potential, which work function, electron affinity, and ionization potential are obtained. And on the right, we have the barriers charge analysis, which the charge transfer between layers is obtained. I don't go into details here. Here, I used this example just to illustrate the Samba code's capabilities. But it is important to highlight that these analysis, plots and projections are completed automated by the Samba workflow. What is the powerful DFT high throughput tool. Finally, I will show briefly some staticals about properties present in the database. Here, in this slide, we can see the twist angle distribution. In panel A, we have histograms that show the emergence of unique angles as a function of the system size. Here, the number of the atoms in the cell. As the system size, the density of unique angles increases. So, in the total database, we have a near continuum of twist angles. We are disponible for analysis. Here, in panel B, we have this distribution of symmetries as a for small cells. Sorry, in this panel, we analyze the distribution of twist angles for small cells when predominant high symmetry angles 0, 30, 60 angles. For the whole database, this distribution is esqueci como que fala, more distribution. Sorry. Sorry, porque eu preparei o meu slide em inglês só dessa parte aqui, E o meu tempo dava antes de eu começar ele, Então, assim, I will skip this slide, and finish my presentation, E before the questions, I want to say I will still improve my English, So I prefer questions in Portuguese, but I can try answer questions in English if needed.
Thank you, Augusto. The session is now open for questions.
Valeu, Augusto. Vocês têm restrição das simetrias ou interesse particular, ou foi aquele conjunto de sistemas? Você combina, a maioria é hexagonal, Célula unitária hexagonal com retangular ou quadrada, aí o critério é só o strength que vai caber em 3%.
Vamos selecionar materiais. Nós nos focamos em selecionar materiais bidimensionais, com interação Van der Waals, mas assim, os que mais são citados na literatura. Então, depois que a gente selecionou esses 63 monocamadas, a gente percebeu que a grande maioria são hexagonais. Então, não foi um foco na simetria, foi uma ocorrência natural, que a maior parte desses materiais 2D são hexagonais. Entretanto, existem alguns exemplos retangulares, né, no nosso database.
Mas você faz bilayer, onde um é hexagonal e o outro retangular?
Sim, no caso a gente analisa todas as combinações de todos os materiais presentes, de todas as 63 monocamadas. Então tem sistemas retangulares com hexagonais.
Que esses talvez sejam os mais interessantes, poucas pessoas estudam porque é mais difícil fazer modelos, né?
Porque geralmente existe uma regrinha, né, para o casamento de rede entre células hexagonais. Mas aqui a gente usa meio que uma força bruta, né? Compara todas as células possíveis.
Oi, Augusto. Muito bacana a apresentação, é realmente muito útil todo o trabalho que vocês estão fazendo. Inclusive, até na pergunta do Gabriel, eu venho trabalhando também com sistemas Twist em rede quadrada e retangular. E vai ser muito bacana acompanhar o desenvolvimento também, porque eu acho que vai ser útil durante o projeto. O que eu ia perguntar é em relação ao mismatch, né? Ele é calculado em relação à deformação de uma rede, de uma das redes, só para confirmar.
A gente usa vários parâmetros de mismatch, né? Igual, por exemplo, aqui é um exemplo, sei lá, de duas células, por exemplo, quando eu faço esse loop de comparações, né? Em algum caso eu estou comparando essas duas células. Então a gente usa vários parâmetros de mismatch. Uma, né, é se a variação na área entre as células ela for menor do que uma determinada porcentagem, né? Mas o que é mais, assim, importante nesse caso, né, é se o módulo dos vetores de rede e o ângulo de abertura entre eles é menor do que uma determinada porcentagem. Porque isso aqui é o que vai dar o formato da célula, né?
Tá, entendi. A pergunta na realidade é se você tiver o tensor de estresse, o tensor de elasticidade do material bidimensional, se isso poderia ser usado para ponderar o mismatch, porque aí a gente vai estar falando da força necessária, né, e não só da deformação.
Nós não analisamos esse tensor, né? Mas assim, pra ver, né, essa questão da força, né? Mas assim, no caso a gente, no nosso conjunto de dados a gente salva, né, todas as matrizes, né, de supercélula e de deformações que foram utilizadas, né? Então qualquer coisa a gente pode, sei lá, utilizar para fazer um refinamento das estruturas selecionadas. Mas a princípio a gente não olhou para esse tensor.
Okay, no. To stay on time, let's thank again the speaker. The next speaker is Marcelo Albuquerque. Okay. So Marcelo is going to talk about less is more. How choosing data properly influences machine learning-based outcomes.
Yes, good afternoon, everyone. I'd like to first thank you for the invitation and for this opportunity to be here talking about this work within the INCT project. And yeah, this is not a holy grail, but it's a hope that we can, there is some work that show that choosing good samples may give you good outcomes from machine learning based models. So yes, my name is Marcelo Albuquerque, and I'm supervised by Professor Márcio Costa and Rodrigo Amorim at UFF. And first of all, I'd like to introduce myself because I'd like to be known for people. And I'm from Pernambuco, which is northeastern Brazil. and very well known for Frevo and Carnival. And it's a popular feast, festival. And then in 2010 moved to Rio de Janeiro, start my graduation. And then I did my initialization in scientific stuffs, master's and PhD with Pedro Venezuela, where I study defects and oxidation materials, 2D materials. And then started to do multi-scaling modeling, molecular dynamics simulations and DFT calculations. Interchangeably. And yeah, this is the other side of the view from the building. Tariq showed yesterday the other side. So over there we can look at the sugar loaf, but we cannot eat it. And over there is the Christ, where you can visit as I did. And then in 2021, I went to Uppsala University, where I met Ramon, that presented yesterday. And my supervisors, it was a joint project between Sweden and Brazil, from CAPES. And my supervisor was Luciano Costa from Institute of Chemistry at UFF, and Professor Daniel Brandel. And this is one of this department, Armstrong ABC, is one of the biggest or more well-known battery center researcher facility in Europe, and also had collaborations with Professor Reza Ionesi and Wessel van Ikeren. Then I came back to Institute of Physics at UFF with Márcio Costa and started the project at over there. And right now I got this call accepted, approved. And yes, and I'm about to start this new project, which is called an efficient electrolytes for sodium-ion batteries from artificial intelligence to multi-scale simulations for the sustainable development of energy technology. So everything that I have learned so far will be really good, and we have collaboration with Brazilian people. Professor Rodrigo Capaz accepted, Lydia Carvalho as well, and I'm very thankful for them. And also Julio Guedes from CNPEM, which is a center of mineralogy at Rio de Janeiro. And the collaboration for abroad, people also accepted to participate. And yeah, this is the outline of my talk. I forgot to start the time, sorry. And yeah, so basically, yes, I'm within the DFT and molecular dynamics simulation range of methods that can be applied in scientific materials and in material science, sorry. And yeah, so DFT is well known and really good because of its accuracy, while molecular dynamics, you can extend the time scales and also the size of the simulations that you want to investigate. And within machine learning, interatomic potential, we can bridge these two things, where you can have larger size of materials of system and simulate longer time scales with the accuracy of DFT, from DFT, okay? And yeah, this is the second law of Newton's second law. And yeah, basically you have a material, and the way you can get the potential to solve the equation is to get the bond stretching, for example, then the angles, then the dihedrals between these atoms that are labeled over there, and also the non-bonded interactions. And this is the so-called first generation, or we can call it like that, because bonds are not breakable. We keep the guys as they are. And then we had the second or third, I don't know, people sometimes change the namings, and generation, where people started to come up with new potentials, where they include also the breaking the bonds the breaking of the bonds. And then we have this new generation, which is the materials modeling from data and from statistical learning, which is the machine learning interatomic potentials. So this work, my motivation is the following. Usually people use a huge amount of data to do something like this. For example, they get like more than 17,000 configurations, and out of them they choose about 5,000 configurations to build the gap model. And yeah, this is the full configuration that they choose. Everything stable, everything good, everything nice. And yeah, they have like, this is called the carbon, the potential for every carbon materials. They call it like that in this paper. And then this paper also caught my attention from Luana and Márcio, Luana Pedrosa, where they say that they show that the structural properties are less dependent to the size of the training data compared to the dynamical ones. And a good sampling also is important. And they show that the error, I mean, it doesn't matter how many, apart from 10% of the training data set, you have your error almost insignificant. So yeah, not only sizing, but also quality matters when it comes to choosing data to build these kind of things. So graphene, my idea is to study mechanical properties of these materials. And yeah, this we have like a graphene sheet here, and this part is kept here. This is like how the simulation takes place. The experiment takes place. And then this part here is continuously moving until the breaking happens here, in this part here. And this is something that I found in the literature showing the stress. And there are some kinds that show different values, but experimentally they found about 130 gigapascal, where the stress is the rupture stress, about here. And the other material that I'm interested in is the tungsten, because when they start to build the tungsten over a silicon oxide substrate, they found that depending on the width of the material, different phases start to appear. And the most common ones are the stable ones are the alpha and the beta ones, which appears here. But also when we change the temperature and the pressure, depending on how they are built, you have also these two phases happening. And my idea is to study these guys as well. So we have a 2D material and a 3D material, but this is a bit behind the 2D material one. So I have to leave these results for the day. So the way I started to build this model is to generate 21,000 initial configuration from using simply GROMACS simulation package. So the way I did that was choosing different force fields. Thanks. Different force fields, and using different temperatures for each force field, because we have different parameters for each of them. They were built thinking on different systems or different properties they would like to extract from the simulations. So there are different parameters that can give us different results. So this is one of the ways that we thought that we could get a good sample for the material. And also the temperature, because you have different velocities associated, and this will like change a lot the things. And from apart from this, I also removed sequentially. I removed the dihedral, the angles, only keeping the stretching. And yes, and all this stuff gave me 21,000 initial configuration, but the things that how can I choose the good ones? I mean quotes for that. How can I choose the configuration properly? Because I don't know if they are similar, if they can oversampling my model. So I use this HDBS scan, which is a clusterization technique, so that I can choose proper things to analyze. For example, the root mean square deviation and the average of the fluctuation of the atoms along the direction perpendicular to the surface. And unfortunately, depending on how you choose these parameters here, the clusterization is not that good. I mean, it's poorly clusterized. So I tried different stuffs, and the standard deviation of the fluctuation gave me better clusterization. And this is how they are numbered. And this one here, they are noise data, which is data that didn't belong to any of the cluster regions. So just to show a few of them, we can see that, in fact, they are pretty similar. I mean, configuration-wise. And this is other region where you can see that they are almost plane. So I think it did a good job. And for tungsten, I did something similar. I chose these 4 different guys, ranging from 300 to 4,000 Kelvin, where I choose this range because the melting point is about 3,000 something Kelvin. So yes, just to show how the RMSD changes depending on the number of atoms that is around the specific atom. So I can see that, for example, for the specific coordination number, we have a whole different position that the atoms can occupy. So depending on the temperature, the blue one is for 300, they are pretty close to each other, and for 400 Kelvin, they are pretty sparse. So yeah, but this I will have to show you later on another day. And then I tried gap model and DeepMD. The gap model didn't work that good, as you can see. So I trained on 3,210 most representative configuration out of those ones that I showed before. And a comparison with a model trained on only this number here. I mean, just to check. And they were pretty badly. And for the DeepMD, I will run a bit faster here. Train on this amount of data. This is the architecture that I used. Although the loss was good, the simulation crashed, didn't work. But when I used larger data, 3,000, more than 3,000, using similar architecture, the simulation kept, even for supercells. And even for more larger supercells, it worked really good. And even for nanotubes, it worked as well. But for nanotubes above, at this temperature, they crashed. But at 1,000 temperature, 1,000 Kelvin, it worked. Have in mind that the melting temperature is below that. So I think it's a good stuff. And yeah, now this is the result compared to A-Ribble. And this is the pair distribution function between the atoms. We can see that they are pretty good, comparably, given the size and it's pristine graphene. It is a pristine graphene with 112 carbon atoms. So this is a 6x6 supercell. I mean, more than 4,000 atoms here, and they work pretty good. And the stress curve gave me, quantitatively good results, but qualitatively bad results, which means that I need to improve by putting, I have some things on mind. I need to improve the models, the model by improving my data set, but the value is within the one calculated by Ariba. It's good as well. And this is imagine that bond is like rotating within 20 degrees, like rotating over there, and this is the distribution of this angle depending on the strain applied. So we can see how they are distributed, and at some point the things simply get messed. Just to show you, and this is how this bond is distributed, lengthy. So up to a certain point, the results are relatively good, but then it's not that good, which means I need to improve. So I will skip this part. I will talk about some collaborations. I will skip this part. This is something that we did with Tatiana Rappaport and Luis Canônico Armas, which show that the charge transfer between carbon and MeO_2 heterostructure influences how the X-ray absorption changes, and this is comparable to what Adriana Figueroa and Venezuela did for the experiments, and they would like to understand how this works. So there is charge transfers that happens when the graphene layer gets close to the MeO_2, and this also has to do with non-covalent interactions that changes as they get close. So just for you to show this other collaborations, I will skip this one. And in conclusion, just show you that changing temperature and changing the ingredients of the classical force field to build the configurational space, we can have a good sampling as long as you choose good representatives of this sampling. Here I choose the root mean square deviation and the standard deviation of the fluctuation of the atoms. And the result on the stress strain curve was not that good qualitatively, but was good quantitatively, and was very comparable to our Ariba potential, which was built to study this kind of thing. So just a video. Things are pretty nice, and our perspective is improving the model, as I just said, and also comparing the results with that gap that I showed before, the full stuff that I showed at the beginning, and also use this step 0 for carbon nanotube, and also try to improve that I believe that will give good stuff for us. And this thing here that I discovered a few months ago, it's known, I forgot what this means, ion potential, outperforms existing model with up to 3 orders of magnitudes fewer training data compared to other things that exist. So I'd like to see that. I saw a paper that used this technique here to come up with Hubbard parameters, but they also use it apart from configuration, position, and forces and energies. They also use the electron occupation of specific orbitals. On Tungsten and also this kind of stuff. I'd like to thank you. If you have a question, I'll be very happy to answer you. And thank you to all the institutions involved. This is from the IQ, Institute of Physics, Institute of Chemistry at UFF, the INCT Materials-Informatics group, CNPEM, and then a final piece is that in October this year, we would like to see you at UFF and to have the 19th Brazilian School of Electronic Structure that will be held there in Niterói. And yeah, don't forget the deadline for the subscription is 25 August, sorry. Yeah, thank you very much.
Thank you, Marcelo. We have time for one quick question. It's good. I can exercise, right?
Oh, thank you very much for the talk. I would just like for you to clarify a little bit about what was the parameter that you used to do the clusterization algorithm. Was it the mean square displacement of the atoms? Oh, okay. That's right. Okay. Oh, okay. So like 0 Kelvin. Well. Okay. The first configuration, and then it. Okay, yeah. Okay. I understand. Thank you very much.
Okay, so to stay on time, let's thank the speaker again. And the next talk will be given by Lídia Carvalho Gomes. And the title of her talk is Defects in Semiconductors for Renewable Energies, exploring the pi phase of sulfur. I don't think so. Okay. Okay.
So hi everybody, and I'm really happy to be here in our second annual meeting and share a bit of the work that we have been doing. So we have been exploring defects in this new recently discovered pi SCNS phase, so a thin sulfide. And as you see, we are not working here with like machine learning or related techniques. We are doing for now pure DFT calculations to explore defects in this material. But I want to share that this work was actually born from this INCT. And starting from Luis, who is the student who is doing all the hard work, all the calculations. He's now a master's degree student with me. But he started to work with me as an undergrad research with a scholarship from this INCT. And he was working a different project actually. And last year, when we had our first annual meeting, we were discussing with Pedro, and he mentioned about this new material that I haven't heard about it by then, and I found it really interesting, and since then we have been working on this. Okay, so this is the material. It's like it's a binary compound of this thin sulfide family. It has a cubic structure. We'll talk more about it later. And about 10 years ago, by this group, they have solved its structure. And since then, people have been looking a lot to this material as a possible photovoltaic PV material with good properties. And then why renewable energy? I hope I don't have to convince you how important it is to put efforts on developing new materials and technology to generate clean energy. But I just want to quickly mention to you that since the Paris Agreement 10 years ago, So a couple of countries have set this goal to limit global warming to 1.5 degrees Celsius above pre-industrial levels. Above this, we can have like catastrophic effects for the world. And unfortunately, last year IPCC came up with this data that actually last year we have reached this temperature. So it's really urgent that to continue putting efforts to develop this area. Okay, so just coming back in time a little bit, this material, this tin sulfide, this family of materials, maybe the most known member of this group is the alpha phase, this one which has a orthorhombic structure. It has been known since the 60s, and a lot of groups have been extensively studied this material as a good candidate as a photovoltaic material, mainly because of its optical properties. For instance, band gap falls in the optimal range for good to achieve maximal theoretical efficiency. It's a naturally occurring material, so non-toxic and abundant elements. But still now we have very low efficiency with solar cells made of this material. So by now, it is one of the most recent results. Can reach something about 5% efficiency with this material. Very low if compared with more popular photovoltaics like SIGs and cadmium telluride. And most of this low efficiency it's attributed to defects, anisotropy, and even the difficulty in finding good contacts for this material. Okay, so 10 years ago, this group have solved the structure of this new member of the thin sulfide family. So it's a cubic structure with 64 atoms in the unit cell. This one has 8 atoms in the unit cell, so a bit more complex. It has a larger band gap, something around 1.7, 1.8. There is still some debate if it's direct or indirect band gap, but the difference is actually quite small between them. I'll show later in some band structure calculation. But it's a metastable state actually, but very low energy above the more stable structure. So it can be stabilized. It has been synthesized by a lot of groups. So it's still a very poorly explored material in the literature. There are some theoretical indications that can have higher optical absorption compared with the alpha phase, which is good for solar cells. But its applications, possible applications come beyond photovoltaics. It's a non-centrosymmetric material. So this material has only rotation and screw symmetry axis. So it's expected things like piezoelectricity and nonlinear optics, this material, still not explored in the literature. And another thing that is really important but it's not explored, is what we are trying to do here, is to investigate the impact of defects in this material. In particular, how defects can affect the optical properties for this material in particular. So this is what we are trying to understand here. So one of the motivations for this work was actually from this experimental group from the UFMG from 2022, from Professor Rogério Paniago. They have explored the electronic gap in thin films of both alpha and pi phase thin sulfides. And they have investigated like a large number of samples, and they see that for the alpha phase they have a very large variation in the band gap. So it doesn't seem to be very controllable, the band gap size in this material. For instance, we can see that the band gap that they measure can vary from 0.6 to 1.8 eV. While for pi SNS, the band gap that they measure is way more uniform. So they have constantly found something more around 1.7 eV. So it seems to indicate that the band gap and then maybe the optical properties can be better controllable in the pi phase. So it's not well understood why they have this difference in the band gap. And one thing that they claim is that could be because of defects. And this is one of the things that we are also trying to understand. So the results that we have so far are still ongoing results, as you see. So we still don't have the answer if this is because of defect, but we hope we can give some indication, some direction in the short time soon. Okay, so to investigate the defects in this material or other materials, for those who are not familiar with defect calculations, it requires a large number of calculations, as you see here. I try to give a very quick overview. And so it's very convenient to do this, use these pre and post-processing tools. We are using here one called Doped. It's a Python-based tool that can help us with the pre-processing, generating defects, and suggesting possible charge states, and also the post-processing of the calculations. So generating and calculating formation energies, defect diagrams, and also doing all the thermodynamic analysis like defect transition levels, carrier concentration, Doppler limits, and so on and so forth. So for our pi and CNS phase, this is just to give an example of the defects that we are looking at. So we are working here, we investigate vacancies, antisides, and interstitials in this material. So in principle, we'd have to do at least 280 calculations. And to try to make this a bit more fast, we are trying to focus on the low energy defects. So we did one quick calculation for all of these defects, only that the gamma point calculation, all of these using DFT. And then we narrowed out to something around 100 calculations of defects and the charge states. These are like 8 vacancies, 8 antisides, and 8 interstitials with their relevant charge states. Okay, so just to give it also a quick idea, what we want here is to compute the defect formation energies of different defects in the relevant charge states, because these defects are usually ionized defects. And to do this, we usually use this expression which we compare total energy calculations of a supercell with the defect that we are interested in, and compare with the bulk, the perfect material. And then to take into account a different number of elements to create a defect, we need this term, which is the chemical potential for phase stability. And to take into account the different number of charge, when we have an ionized defect, we need to take the electrochemical potential term into account. Okay, so also to give an idea for those who are not familiar with this, these results are usually compiled in what we call defect diagrams, where we plot the defect formation energy as a function of the Fermi energy. As you see, this is a linear relation. The slope of the curves is the charge of the defect. In this way, neutral defects will have like horizontal lines. Donors and acceptors will have positive and negative slopes. So for a given material that we are interested in, we just do calculations for all the relevant defects in all their charge states, and we put this all together in the defect diagrams I will show for PySCN in the next slide. And from this we can have information like the concentration of defect that we expect for a given synthesis condition, for instance, and also from the charge neutrality condition. So this expression here that basically says that the number of electrons in hole, free electrons in hole in the material will be proportional to the concentration of defects times the charge of each defect. And from this we can define the position of the equilibrium Fermi energy, which is the Fermi energy of the semiconductor, and have an idea if the semiconductor is an intrinsic, p-type, or n-type semiconductor, things like that. And another term that it's important here is this one on the chemical potentials. So for each material, we have a range of chemical potentials of our material, where our material is stable. It's basically controlled by the synthesis condition that we are applying to grow our material. For PySCN as phase, so Luis has generated the phase diagram, the chemical potential space. So we see that the range of chemical potentials where our material is stable is this one. So these values for the sulfur chemical potentials, and this one for the thin chemical potentials. So this is the stability regions for Pi. as CNS. And from this, we can then identify regions like SN rich, where pi-SNS is equilibrium with thin bulk thin, and SNS poor conditions, where our material is then stable, it's in equilibrium with this another thin sulfide material, thin disulfide actually. So we can actually nowadays control very well if you are growing our compound in a thin rich, for instance, or thin poor region. In this way, we can control the defect formation energies and all the defect physics in the material. Usually people do this like with methods called, one of them is called phase border mapping, where they grow your compound with a very small amount of secondary phases, and then they can pin, like they grow where they are growing these materials, and they can define very well the concentration of the defects and the nature of the carriers in the material. It's a very nice way to control carriers and many different properties in the material of interest. Okay, so having defined our stability region for our compound of interest, we usually plot the defect diagrams in these two extreme sets of chemical potentials. Here I'm showing the defect diagrams in the thin poor and the thin rich conditions. So I know it's a lot of information here. So we have all the vacancies, antisites, and interstitials that we have calculated with all the different charge states. So I try to just to give an idea of the main results, what we should focus here. So what we see here is that in terms of defects which are dominant in these compounds, 5 minutes? Okay, thank you. The defects which are dominant in these compounds, we can see that in both growth conditions, vacancies dominate. So vacancies are these bluish lines like here. So in the thin pore condition, we have thin vacancies that dominate and then bring this material to be a strongly p-type material in this region. And this is actually very similar to the alpha phase. So alpha phase is very known to be a very strong p-type material, mostly because of thin vacancies as well. But one thing that is different here from the alpha phase that we identified so far are the presence of low energy interstitials, which are these like pinkish lines over here. So these are different interstitials defects. And we see that for the alpha phase, if you remember the structure, the alpha phase, the atoms are way more packed, they are close to each other. So it's really difficult to put interstitials there. They usually have higher formation energy. But for the pi phase, this structure is a bit open if you compare with the alpha phase. So there are some regions with a very large space where you can easily put interstitial atom there. And then in this material, these interstitials, they have lowest formation energy and are expected to be observed in higher concentrations. And what happens here is that these antisites, they actually promote a less p-type behavior by giving electrons to the system. Okay, so it makes it the pi SN more less p-type if compared with the alpha phase. Okay. So in terms of the carrier concentration achievable range, and this is actually important for solar cells applications because there is an optimal range of carrier concentration that we want. It can be too low, lower than 10 to the 14 carriers per centimeter cubic, because we have poor electrical conductivity in this case, like weak absorption and enhancement and other things. And the carriers can also be not too high, larger than 10 to the 18 carriers, because of the increased recombination, decreased carrier lifetime. So we want something between 10 to the 14 to the 10 to the 18 carriers, and these kind of calculations can actually give us some idea of where to grow our material of interest if you want it to be applied as a solar cell, for instance, a photovoltaic material. And you can identify here that this is the optimal range of carriers that we are looking for. So if you want to apply this as a photovoltaic, maybe you want to grow it in this region. So I forgot to mention this is the chemical potential axis, how we change the chemical potential axis in terms of the annealing temperature when we are synthesizing of our material. And then we would have to grow this compound in this region here to have good carrier concentration. Okay, so just to finish here, I want to mention this result that we found for a particular defect structural transition from the particular interstitial. So this is the defect diagram only for some interstitial defects that you look at it. So for this one in particular, what we found was that, so this is the sulfur atom that is the extra atom to build the defect. And you can see that if it's positively charged, like +2, +1 or neutral, this defect has this configuration. The sulfur forms a bond with the host sulfur. But if you start to keep putting electrons in the system, raising the Fermi level to this direction, it has a structural transition between this defect. So this bond is actually broken, and the sulfur make the bond with only the 4 thin atoms around it. And why this could be interesting or important to look at, this is just to see like the difference between the two configurations, the bonding being formed between the sulfur atoms. And it's because of the huge impact in the band structure and expected also huge impact in the optical properties. So this is all band structure, PBE band structure, so underestimated band gaps. But we see that upon the inclusion of these dual interstitials, there is a large decrease in the band gap, and this charged state actually makes the material be a metallic compound. Okay, so if you can control the Fermi level and then control the charge of this defect, we can control and change a lot the optical properties in this material. Okay, so just to finish here, I want to give some very quick understanding of why these bands change so much. And to this we do this COP analysis. Not going into details because I'm running out of time, but just give an idea of how strong, how are the bonds between these two atoms here. And then we can see that the formation of the bonds between these two sulfur atoms, what it makes is like strong bonding and creates a bonding and anti-bonding state, pulling the bands up in energy and then closing the gap when comparing with this other defect here. So next steps for this work, we want to further investigate these interstitial defects. You see another possible interstitials that change upon the control of chemical potentials and see the impact of this in the optical properties, and also see some alloying. There are some information in the literature showing that optical properties can be improved with alloying, optical properties in general, and also do this selection metric calculation to really have information about the potential efficiency of this material for photovoltaic-like diversity material. With this, I want to acknowledge the INCT, and also Luis and Pedro for all the discussion, and all of you for your attention. Thank you very much.
Thank you, Lydia. We have time for one quick question.
So Lydia, can you go back to the formation energy graph? So the two questions. So one, you have a negative U there somewhere And so do you understand this one that goes up and then straight? And
Negative what? Sorry.
negative U, it goes directly from -2 to 0.
This one.
Yes.
Okay.
So there is no the +1 slope.
We just eliminate the higher energy, so we put them all them together, and the ones which are high in energy we don't show in the defect diagram, because in this Fermi energy range, this one, the neutral defects will be stable, like the -1 or -2 charge defects will not be stable, so we just eliminate them from the defect diagrams.
Another thing that caught my attention is that there are some defects that are both positive and negative.
Yeah.
So this is kind of unusual. So can you briefly comment on that?
Yeah, this is actually
how
very-
you thought about this?
You mean, for instance, this one? So, yeah, for this material, both for the alpha and pi phase and other materials as well, some defects can really have many different charge states within the band gap. So it really depends on the material and the defect that we are considering. In this case are the interstitials. They can really assume a large number of charge states.
Great. So let's move on and thank the speaker again.
Thank you very much.
So the next and final speaker for this session is Alberto Torres Riera Jr. And the title of his talk is Machine Learning Potential for Structural Properties of Hematite.
Hi. Okay, thank you. So I'm going to show you some. We have seen some talks about machine learning interatomic potentials. Here I'm going to show some work that we are working on applying machine learning potentials for hematite. So this work is done in collaboration with researchers from the Federal University at Ouro Preto and from the company Vale. So, okay, hematite is iron oxide. Here we have the structure of hematite. It's primitive and standard unit cells. So it has, it shows a complex behavior. Sorry. It's a very important material. Now, obviously, it's our main source of iron. So here in Brazil, especially, it has a huge economic importance. It's also studied in the context of catalysis, specifically for water splitting. So one of these behaviors that hematite shows and displays. Its potential energy surface is dependent on the atomic, on the magnetic, the magnetic structure of the magnetization of the iron atoms. So depending the material is antiferromagnetic, how the spins of the iron atoms are aligned organized. You have different surface potentials. Here, in our case, we are kind of try to ignore this. We turn a blind eye to it and just stay in the lowest potential energy surface. And one of the things that we are interested in the mechanical properties of hematite that very surprisingly have been very scarcely studied in the literature. So just to give you, this is a quick overview of the measurements and works that have been done in the literature. So you can see the measurements and calculation of the lattice constants and the elastic moduly. So we can see here the numbers in the parentheses here indicate the number of works. So we can already see that we have really few works that have been focused on this material. And here, these are the distributions, the value distributions of the measurements and theoretical calculations. And here, there is something, these dots here, with these error bars here, these thick error bars, is what you call a consensus. That is a median estimation of the results. We are going to use this to compare against. So just. Okay, so for the elastic constants, we have even less works that have been measuring or calculating the elastic tensor constants. So this is basically the elastic tensor is the generalized Hooke constant. So basically you have 7 works that have been or measured or calculated. There is a problem with the work of Voigt that was done low quality sample. So in these 2 works were actually fitted to the data of Voigt. So basically you have only 4 works that have investigated its mechanical properties, the elastic tensor constants. So, okay, our main goal or long-term goal is to develop machine learning universal potential, but universal here is a little universe for hematite. Well, hematite and obviously interacting with other materials. Now here I'm going to show you only the work with hematite, specifically focusing on its mechanical properties. And obviously, we also want energetics want to know if or how well or bad the surface of the material, for example, interacts with other materials, for example. So, okay, just a quick overview of the methodology that we have here. As Marcelo has shown in the talk before, we have first we sample the configurations that we will introduce density functional theory plus a Hubbard 10 for the iron. We then train machine learning potential using the code maze. This code, I'm not going into details here, but uses graph neural network potentials. This type of architectures are really well suited to represent atomic structures like molecules and materials. And then we perform our simulations. Okay, you haven't seen actually in the tutorial this morning. This is kind of the pipeline to build machine learning potential. So we sample. So the method that we use to sample our configuration is applying molecular dynamics with various thermodynamical conditions. And one thing that we realized is that we also had to generate configurations applying strains and random displacations in relation to the equilibrium geometry, and this actually helps improve how the potential can describe the elastic properties of the material. Then we do, obviously, the DFT calculations. We take the energies, force, and stresses. We train our neural network, and so on. So here I want to show you. This is energy pressure diagram of the bulk structures that we have in our data set for the bulk and the surface. We also include the 001 surface in our data set. So we can see here we have the configurations that have been generated by molecular dynamics and the configurations generated by applying strains and random displacements. For the surface, we only have included configurations applying strains and random displacements. And what we can see here is that especially around the zero pressure here, here are the regions that are important for correctly describing the elastic properties of any material. So it shows the importance of having this type of sampling in our to generate the configurations for our data set. So we have trained 4 models. Here I'm showing you the results for energy, forces, and stresses for one single model. The other ones show performance very similar like these. So all the our models are good. They have energies below the threshold of 1 millielectron volt, and very good forces as well. When we combine our models in a committee, so averaging at the results, we have a small cancellation of errors here comparing with the other models. As for the forces, we get it's a little bit better, it's just a little bit. And an advantage here is that using a committee, we can now estimate the uncertainty of the model. This is something that is important because if you are using just a single model, you can never tell if the model is kind of hallucinating, if it's working, or if it is extrapolating, for example. So now showing you the results of the committee for the elastic tensor constants. So this is how the matrix looks like. Because of the symmetries of hematite, it only has a few independent elements. These are these ones here. And you can see obviously, so comparing to the experiment that we use here is the one of Lieberman that I showed you before for the elastic constants, and for the elastic tensor constants. And here you can see that indeed, obviously, the potential has been fitted to the DFT data, which are the squares here, the squares. For most constants, it is the DFT data, and also, especially for the strongest elastic constants, these ones. it also does a good job compared to experiment. So here we also see a comparison, actually, the same data compared to other empirical potentials already available in the literature. So this is for a bulk hematite. So we can see, for example, that the DFT and maize are one of the ones. Clay also has a good performance. However, remember that this is for bulk hematite. So when you apply these potentials, these empirical potentials for surfaces, they fail completely. So they really don't work. So in order to be able to apply to study surfaces with these machines, we have to resort to a potential that we are developing here. So here I'm showing you for the elastic moduli. Here is a visualization of their physical meaning, and here we can see a rather plotted on star graph of the properties, the bulk, Young, and shear modulus, the compressibility, and the Poisson's ratio. Here, the central hexagon here, that's one represents the consensus of the literature, the median estimations, and we can see that indeed both the machine learning potential that we have developed, which is obviously very close to the density footage computation, that's the one that we have trained on, reproduce well the experimental consensus of the literature, especially compared with the other empirical potentials. So now, well, we have this. We already have 5 minutes. Okay. We already have another versions of this potential, including more surfaces, and our goal is obviously to include other materials as well, so the hematite interaction with other materials. Another thing, like as Marcelo said in the last talk, the tricky part, the really tricky part when you are developing a machine learning potential is the same is what are the configurations they're going to feed into your data set. Doing the DFT calculations and the process of training the machine learning potentials. Sorry. Are kind of it always has its challenges, but it's a, let's say, a known process. So here we're going to do to improve our sampling configuration is to employ also thermal displacements and adversarial attacks, and you actually try to use configurations that maximize the uncertainty of the committee. So basically, it is to implement its sampling protocol. It's already partially already done, and we also already almost finished manuscript that we're going to submit for the results for with this potential. So thank you very much, and it's okay.
Thank you very much, Alberto. The session is now open for questions.
Very nice, Alberto. So I have a doubt, actually. It's not exactly a question. It's general doubt about this kind of training for this type of materials, because hematite is very complex to model even from DFT. You know, you have spin degrees of freedom that can flip, and spin is 3/2 at some point, then it's 1/2, then another one, so it fluctuates over time and structure. So have you thought about that? How can you handle with that? Would it be possible to train a machine learning? So besides total energy, forces and positions, you put spin as well?
Yes. The first, like you said, it's a complex material. It has this. Actually, the potential energy surface depends on the magnetic configuration of the system. We solve this problem by not looking into it. Firstly, that's not a problem. That's the best way to. For us, that's not really a problem, but one of the things that we are looking into is exactly that, to include, to solve, to include the spin degrees of freedom in the training, so the neural network is going to be receive that as an input as well, and also to predict the magnetic state.
Any other question?
So, as Gustavo said, this is a hard problem where you don't want universal things because you can't. But did you do a preliminary screening on your DFT? Because you're focusing on mechanical properties. So even the functional plus U or not plus U, these would change more the mechanical properties than how you fit the potential if your data set is good enough.
Yeah. For the things for the bulk, it changes a little bit, not that much. However, we want also to include surface and materials interacting with the surface. So then we need to have the more correct electronic structure to be able to describe the interactions. Also, another thing that, so going back to something that Gustavo was asking about, you have also the thing about the oxidation states of the iron atom. We have, I haven't shown here, but we have tested this potential with magnetite. It shows mixed valence oxidation states. The potential also works for, not as well as for hematite, but it also works for magnetite.
For your mechanical properties, the matrix, how little are you saying? 3%, 5% when you change functionals? You mean it doesn't change much, but how much? 5%?
I couldn't tell you now.
Because when you go to surfaces, it will only get worse. So if your baseline is 2%, hard problem. Thank you.
Okay, so let's finish the session. Let's thank again the speaker. And an announcement, we will take the official INCT meeting photo right now before the coffee, so we can all join over there to take the photo. Thank you.
The next session will start the third tutorial. Then now, so please come to the auditorium. The ones that are interested in the tutorial, please come in now. We'll start. Hello? Troca pro computador, por favor. Eu vou lá fora chamar um pouco.
Então, cadê ele? Tá aqui o Jorge.
Good afternoon. So now we'll start with the third tutorial. So it will be given by Christoph, Elia, and Suban. This tutorial will be about machine learning interatomic potentials, active learning techniques. So you start, Christoph. So go on.
Okay. Few remaining brave souls. I'm happy to see you. I'm Christoph. I'll be giving a few introductory slides on active learning, and then I have Elia with me in the green jacket and Shubham in the white jacket, who will be giving the worked part of the tutorial after. So let me start with a question or a survey. Who of you has ever trained and used a machine learning potential in a simulation of molecular dynamics? Okay, yeah, well, the Hamburg people, probably all of them, but okay, some people. So if I ask who has ever trained a committee of machine learning models and that did active learning, I will probably see no hands, right? There's one hand. You don't count, Alexandre. Okay, so that's an opportunity for you to learn something new. I think the tutorial is going to be quite simple and quick. Essentially, the only mathematics you need to know is how to calculate a mean and a variance of a distribution. So that's I'm sure everyone can do that. Okay, so these machine learning potentials, what are they? So as we have learned in the first tutorial yesterday, we want to run simulations of molecular dynamics. We want to evolve molecules in time, potentially decorated by path integrals for quantum nuclei using classical equations of motion. So this is the mass matrix, acceleration, and the force calculated as a gradient of a potential energy surface. And what we want to do in order to achieve big accuracy in our simulations, we want to calculate these potential energy surfaces from quantum electronic structure by solving the electronic Schrödinger equation via the means typically of something like along the lines of density functional theory. This is typically very expensive, so we are limited in size and length scales of our simulations, and we want to let's say maintain this accuracy of DFT with something much faster, and this is the place for machine learning interatomic potential. So in this tutorial we are going to be talking about neural networks, and you have already learned this morning that neural network is nothing but a function of an input. That is our structure, parameterized by a set of parameters that we call theta. This gives us our energy. These parameters you have also learned this morning. These are called weights and biases, and these tell us how the individual neurons are connected together in the structure of the neural network. So when it comes to training a neural network, we are facing an optimization problem in the space of these parameters, theta, right? These weights and biases. So typically we have something, just a scheme, but we have some many-dimensional hypersurface on which we are optimizing. And how we typically do this, we define a loss function L that is a function of these parameters, and a data set D, and we are looking for the minimum. I will mention an important point that will be important later. These hypersurfaces are often very, very complicated in structure and contain many local minima. It is not necessarily our goal to find the deepest global minimum. It's good if we do, but it's not necessary, because we can also end up in a, let's say, higher lying minimum. That is, if it's low enough, it gives us low enough error in our model, we are happy with the prediction. That's it. And it also gives us a great flexibility that I'll talk about later. So just please remember this point. So now I have said on the previous slide that the loss function and of course by proxy also the neural network model itself depends on the training set that we have called D. And here I would like to ask what do we require from this training set, right? So first we require uniform and dense enough coverage of what we call the thermally available configuration space. So we need the model to be prepared for any kind of configuration that it can meet in a simulation that it'll be asked to run later. So here's a analogy that I really like. So this thing is a wedding tent, right? And so our potential energy surface, our energy as a function of nuclear positions, will be represented by the fabric of the tent. And of course, this tent requires these tent poles, right? These poles that support the tent. And we need to position these tent poles uniformly and dense enough so that it can support the fabric of the tent in all the right places. And these would be our training structures, right? So what we need to remember also is that we have two regimes of prediction. We have interpolation and extrapolation. So interpolation would be if we ask the model in this analogy to predict somewhere under the fabric of the tent, and we are typically happy about that because the models are very good in interpolating. If we ask the model to predict somewhere in these bushes, it will not be so great. Yes? Was there a question? No. Somewhere outside of the tent, the model has to extrapolate, and this is typically where neural networks are not so good. So if we were to predict somewhere outside of the tent, we need to extend the tent by extending the training set so that it also covers these places. And what we also want from our training sets is for them to be compact and robust. That means as small as possible and as contain as much information as possible, right? And so the simple way how to do this, given a pool of structures, we call this the candidate pool. We want to select structures from this to have this kind of smaller training set, right? And how we can do this in a naive way is that we just do some random subsampling of this. And this will typically give us a training set that is probably uniform, but will not be very compact, because we are not. It's not a data-aware selection, and we don't know which structures are the most important for the training and which are irrelevant. So there's a better way, and this way is called active learning. So this is really nothing else than selection of new training data points based on a measure that we will call uncertainty. We will write this letter sigma for it. And this really is what we want from the model to do active learning, is just for the model to prompt us to know which of these structures have the biggest uncertainty. Those are the structures where the model is, well, it doesn't know what to predict. The error of the prediction is the biggest, and these are exactly the points that we need to add. So here's a little graphic. So we will have some nuclear configuration, some set of molecular structures, and we will have a label of this sigma for each of these structures, and this will, over the candidate pool, this will have some distribution, right? So here I draw Gaussian. It can be something more complicated in shape, but this is just an illustration. And what we are typically interested in, is these structures here. So these would be high sigma outliers, because these exactly represent the structures that we have to learn, that we have not yet seen, that we have not yet learned, and we still have to. These structures here, not so interesting, because the model is already very certain what the prediction should be. So we can do this in formally two regimes. So the first one is quite easy. When we have a labeled candidate set, so we have a bunch of structures, and we know in each structure what the energy and the forces are as calculated by DFT. And we want to kind of filter this set, restrict ourselves to a smaller subset on which we train, and this we can do with active learning. In the regime 2, this is a bit more complicated, but also, I would say, a bit more powerful, and this is selecting relevant data from unseen exploratory candidate sets, which are unlabeled. So we don't know the energy and force labels for this data, and based on this uncertainty measure, the model will prompt us to add these data to the data set, but we have to label them before we do that. Okay, so this is in a little bit more detail how regime 1 can look. So we start with some model. For now, we will not really care where we got it. We can just pretend someone gave it to us, or we can imagine, which is typically the case, that we took a few of these random structures, say 10, 20, trained a preliminary model that already has some predictive power. And we take this model and we let it predict outputs on this whole labeled candidate set. So these data have these labels from DFT, from the reference electronic structure method. And we let it predict, and we select these points with the highest sigma, and we add them to the training set that will be a subset of this candidate set. And then we take this training set, we train on this training set, and we get a new model, and we do this iteratively until we are satisfied. I'll discuss what that means a little bit more precisely in a few slides. For the second regime, we have also a candidate set, but we don't have the labels, right? We don't know what the energies and forces of the reference electronic structure are. This we typically obtain by something we call inference from a pre-existing model. So we use a neural network potential to run a simulation. This gives us a bunch of structures, say a trajectory, but we don't know what the labels are because we haven't done DFT. We have done a neural network potential MD, and so we don't know. So what we do, we have some model. We do the same again. We predict the sigma for all these structures. We select the highest sigma structures, and there's one additional step now. We have to take our DFT, our electronic structure software, and we have to predict what these labels are. So we have to calculate what the energy and forces are on these structures that we have selected. The advantage is that we only have to do it for the minimum necessary amount of structures that we are adding, right? So we are minimizing the computational effort that we need to spend on the DFT. And then it's all the same. We add these structures to the training set. We train a model. So the first one I call G, the second one I call F. I'll use it on the next slide, so please remember that. That's the target model. And we have our model F. We do the prediction, and we do this round again until we are satisfied. So this was maybe all very abstract, so I'll try to provide a real-world example from our research work that we have done, and this concerns the thermodynamic state points of water. So for the regime 1, where we have the labeled candidates, imagine we have a trajectory of liquid water, say at 300 Kelvin in the isothermal NVT ensemble, and we run a short simulation of a small system at DFT. This is expensive, but this is how we seed our active learning procedure. We have done that. We use active learning in regime 1 to select structures, and on these structures, these are our training set, and this gives us our model. This would be the model G on the previous slide, right? And then we can use this model to do a simulation. This is called inference, and we can use it to run simulations of liquid water at a large extent for large time scales, with all the benefits that machine learning potential give us. Now, regime 2. We want to do simulations of ice, right? And what we could do regime 1. We could calculate a DFT trajectory again, do the same thing, get a model. But we don't have to do this because model G has been trained on liquid water, but it has a lot of knowledge about what a water molecule looks like, how a hydrogen bond behaves. It knows a lot about water. So what we can do, we can use this model to infer the dynamics of the ice. Will it be a great simulation? Well, probably it will not be a great simulation because the model has never seen ice before, but it will give us some structures that we can work with, right? And so we have lost the slides. Slides are back, good. We have obtained the structures of the ice. We use active learning plus on-the-fly labeling of the geometries. We obtain our model F, that is our target model for ice, and then we can happily use that for inference and for simulations of ice. And we can expand like this, if you wish, across the whole phase diagram of water. And the only DFT, the DFT time we have to invest is on the labeling of these structures. And again, I repeat, this is the minimum necessary number of structures that we need for this training, not more. Okay, so I have talked about this uncertainty measure sigma, right? The problem with neural networks is that once a neural network is trained, it's a function of parameters, and it's the output is deterministic with the same parameters, right? So we put one input and we get one output. This is at variance with maybe the GPR models that Mariana has introduced this morning, which also have kind of naturally measure of uncertainty. Neural networks don't. So what do we do when we want to use neural networks in this way? So I will come back again to this sketch of the parameter hypersurface on which we are optimizing the loss function, right? And so I have said that we can end up in these low-lying minima. We are happy with them. Doesn't matter which one it is, so we can train more models, and we initiate the training of these models. There's some let's say a stochastic aspect to the training, because how we initiate the weights and biases in the training is typically by some means of random numbers. And so we train these models, and we end up in different parts of this plot, right? And we take these models and we call them a committee. So this committee of models. This committee of models is a set of models that have been trained for the same purpose. They predict on the same input, and they give you individual outputs, right? So this we can see here. So we take our Q. This is our molecular structure, a snapshot, if you will, and we feed it into our committee model. We'll call this CNPEM, committee neural network potential, right? And what this gives us is a prediction for each of these individual models. So here NC would be 3, but it gives us much more, right? It gives us an average prediction of these individual predictions, and this is valuable because typically this tends to be a much better estimate of the reference potential energy surface than any of the individual predictions. And crucially, it gives us a quantity that we call committee disagreement, which is the standard deviation of the committee, right? So this would be our measure of sigma. Here is a note I would like you to remember. We call this committee disagreement. we also have another quantity that is called generalization error. That is the actual error of the prediction of the model. So that is how far our committee average, this thing, is from the DFT energy, right? These two are not the same. But they correlate. So a low disagreement will typically imply a low generalization error, and a high disagreement the opposite. Maybe you can, so this is just a sketch, this is not real data, but maybe you can glimpse why there is a correlation between these two. So the black line, this wave now would be our hypothetical potential energy surface reference that we want to measure. So this is something that DFT would give us, right? And we train a committee on some training set that covers a part of the potential energy surface. And as I said, this is our tent pole analogy. Now we are inside the tent, so we are in the interpolation regime. And in the interpolation regime, everything will be close, right? Every committee model will be close to the reference. The average of the committee will be also close to the reference, and we are happy. So this means the error of the model is low, but also the committee disagreement is low, right? But when we go into the extrapolation regime, the committee tends to diverge, right? And since we train these models differently in the beginning, that they will diverge in different ways. So as the further we go, the more they typically diverge. And this means that our sigma grows, our committee disagreement, but also typically corresponds to this dashed line being further from the reference, right? So that's why there is a correlation. Here's an example of how this might work. So this would be, so now the active learning, let me just set some terminology first. The active learning procedure, as I have described before, with a committee model is called query by committee, right? And so this is how it might work. So we start with a ab initio molecular dynamics trajectory. This would be DFT. This is the black line. This is some, I'm missing an axis label, but this would be some potential energy, right? Here. And we see the procedure by selecting a few random configurations, that these black diamonds. We train a committee of models based on this, and we let the committee predict on this same data set, right? And we can see that we get 4 different predictions that are, so for a committee member, say, we get 4 different predictions that have some variance. They are not the same, they are relatively close, but it's not great, because these models, you can see that they are just not very agreeing in general. And so what you do is you calculate the average and the sigma, right, from these predictions. So you get this and that. So that would be the blue line would be the average, and the sigma is the kind of the turquoise shading of this plot. And you pick points that have the biggest disagreement, a fixed number of these points, say typically 10 per iteration, and you take these and add them to the training set, retrain. You can see that you can start decreasing your sigma, and you do this many times, and you decrease your sigma until you are satisfied. Okay, now I have been not completely honest with you thus far. So I have formulated this whole thing in the language of disagreement on energies. And this is, so this would be sigma E. This is the standard deviation of the committee members from, between the committee members. So it's, this expression, you all know how to calculate the standard deviation. I don't have to explain for sure. This is a perfectly way how to build query by committee based on sigma E. But the models also predict forces, right? And you can have the same expression for forces. And so this is a little bit more complicated, right? Because force you have per atom, and energy is a global thing per structure. So this pink thing corresponds to the black thing in energy. So this is the variance of the force predictions for atom alpha. And what we typically do, or what we do in our work, and what we will do in the tutorial, you average this over the frame, and you get a single number for a frame. So this is what we call mean committee disagreement. And it turns out that for many practical reasons, in simulations, force disagreement is actually the key quantity that is used instead of energy, because it is just numerically well behaved and has many advantages. To motivate you a little bit about the physical advantage this has, I will show you this picture. This is a snapshot from a simulation of air-water interface, a water slab, which is kind of bordered by vacuum. And this simulation has been done with a model that is only trained on liquid water structures, on bulk structures that have been calculated in periodic boundary conditions. Right, so and these molecules, or these atoms actually, are colored by this pink quantity, by the force disagreement on each atom. And blue color corresponds to low disagreement, red color corresponds to high disagreement. And we can see that the force disagreement is valuable in the sense that it gives us local information about the deficiencies of the model in each structure that we are trying to predict. So here we see that the model that has been only trained on liquid water structures, like bulk liquid water structures, is deficient at the interface. Of course, that makes sense because it has never seen the interface and doesn't really know what it should do. But this can drive the query by committee to pick structures like this to be trained on. Okay, now the last slide. Before I present the content of the tutorial, I would like to talk about a little bit more specifically about the convergence, what we mean by convergence of QVC. So naively, you could say that it might make sense to set a level of sigma and do query by committee until we drop under that. But that is not the greatest way to do things because, the main reason is because we don't know how much these models a priori diverge and what the value of sigma should be, right? What the threshold value should be. What we want to achieve with query by committee is to extract as much valuable unlearned information from the candidate set, or the candidate pool, as we also call it, in as few samples as possible. So we want to target samples that have let's say the biggest information density and add them to the training set selectively, right? So when does this happen? This happens when sigma for the newly selected batch at each iteration plateaus. That means we are no longer decreasing the sigma in these query by committee iterations and approaches the sigma for the remaining candidates. So here's my artistic impression of what this might look like. We will we will calculate a curve like this in the tutorial, but this is just a sketch, of course. So what we have here is the progress as we do the query by committee as iteration by iteration, right? And this is just the mean force disagreement for each batch of the structures. And this will be the whole set of candidate structures. You can see that this curve is decreasing because we are just adding structures to the training set. We are making the training set bigger, so that makes our model bigger. What is here is the sigma for the structures that we are selecting by query by committee at each iteration. So we can see that we start very high because these are the worst of the worst outliers that you can have in the training set. You add them, you train on them, and the model now knows what these should be. This decreases the sigma as we progress through the iteration, and the difference between these curves, as we are saturating the information that we extract from the selected candidates, there is less and less information, so this separation between these curves is less and less, and eventually everything will plateau. And we are, of course, at every iteration, if you would continue until infinity, we are still selecting from the high end of the distribution. So the blue curve will always be above the red curve, but this will plateau and it will not change anymore. This means that we have extracted all the interesting information from the candidate set, and we can stop the iteration. Another measure which is important to keep in mind, and which is the important thing for the actual performance of the models in simulation, is the generalization error. So once we stop this iteration, we have to take the model and we have to evaluate the generalization error over an independent test set. We have to see what the actual error of the prediction is, right? And as I said, these two correlate. As we do this, the error will also drop. But this is, of course, the error is limited by the information content in the candidate set. If that is incomplete in some way, then we can extract as much as we want, but we will still not get all the information that we need, and we can still get large errors. This is also limited by the architecture that we choose for the model, so it depends on all these things. So we have to check both. We have to check the convergence of our QVC, that is the plateau of sigma, and we also have to be looking at the generalization error of the model. Okay. with that, I would like to present the goals of the tutorial that the guys will take you through. So, we will be not looking on bulk structures, we will not be looking on water ice or water interfaces. We will stay in the gas phase, and we will stay in the world of protonated water clusters. This structure, two water molecules that share a proton, is called the Zundelcation, and it's one of the simplest protonated water clusters. And what we will do first, we will train a committee of maze models. Maze, for the purpose of the tutorial, is an architecture of neural network potentials. Specifically, it is what we call a message passing graph neural network, and you can understand this as a state-of-the-art, really powerful way how to do neural network potentials, and only as a model that gives you you feed structures into and gives you energies and forces out. We will actively select label data points. We will provide a trajectory calculated by DFT to see this procedure. We will actively select label data points for the Zundelcation with query by committee, building on committee of these maze models. Then we will explore the properties and the evolution of the committee disagreement, as we discussed on the last slide with the converging curves over the course of the QBC cycle. And we will try to explore whether we have gained anything with this active learning procedure. So we will compare the active learning selected training set to a random set, and we will see what gives us a better model. Hopefully, of course, it will be the active learning one. So this will be a first part of the tutorial presented by Elia. Then Shubham will take over, and we'll look at a slightly more complicated structure. This is the eigencation. The important distinction here is that here the proton is shared symmetrically between these two waters. Here we have a hydronium cation coordinated by three waters molecule, and the hydrogen bond with these protons is asymmetric. So it's a slightly different structure. It will present a little bit of a challenge for the models and for the active learning, right? So what we will do is that we will take the models that we trained on the Zundelcation, and we will perform an exploratory molecular dynamic simulation of the structure of the eigencation using the Zundel trained model. We will do this in IPy. You already have IPy working, so this should be all good. And as I presented in the slides before, the water ice situation, this is a similar, like Zundel eigen situation. We can expect that the simulation will not be very good, but it will give us some structures and a starting point into more active learning. And we will do this, and we will use QBC with on-the-fly data labeling with FHIMs. This is our DFT software package to improve the initial eigen model and to converge to a model for the eigen that we are happy with. I think that's all from my side. I'll now give the stage to Elia, and I wish you happy computing. Thank you.
Yeah. Okay, don't see anything yet. Okay, so good afternoon, everybody. Shubham and I will guide you through the two small tutorials that we have prepared. If you decide to run them today or in the next day, next week or month, you have two options. The first one is via the virtual machine that we have provided via, you should have received an email with the virtual machine image and all the instructions. If you decide to use the virtual machine, you just need to open it and then get into the documents, tutorials, here you can find also the tutorials of this morning and yesterday, and our is the AL tutorial. So getting into notebooks, you will find two Jupyter notebooks. I will present the first one, the one Zundel, and Shubham will present the two Island. If instead you decided to, let me close this one, yeah, okay. You can get the last updates of the tutorial by git pulling or Gmail. If instead you want to run the tutorial locally, you just need to clone the tutorial. You can find it in the GitHub page of our research group. You just need to Google Sabia GitHub, and here, scrolling down, you will find AL tutorial, and here you can find all the instructions, how to install it, which are the packages needed. It might be a bit memory heavy because it will require you to install PyTorch and some other packages, but here you can find all the information. It will remain online for the next month, maybe forever. So here you can find our emails. If you have any problem, you can open some issues and so on. So we will be available if you need any help. So, okay, as mentioned by Christoph, we will try to explain step by step how to apply query by committee to perform active learning on a really simple system, the Zundel-Katawa. A typical example that can happen in real life is that you get a bunch of structures, usually a molecular dynamics trajectory performed by, I don't know, your colleague. You can find it on materials project and so on. And this one. And you want to train, for example, a model, a machine learning model to use to perform your studies. Usually these these data sets are way too large. You cannot train your models on 10,000 structures. It will take weeks and information is too diluted. We have already seen different talks and tutorials saying that this is not a good way to train models. So we will use query by committee to select a really small, a really tiny data set, really dense information, which contains all the information that we need to then train our models. What we need to do what we are gonna do in this tutorial, of course, we are not gonna run everything on the spot today because training this model takes a while, but we have already provided for you, if you wanna try, I don't know, later on, whether everything is okay. In the checkpoint folder, you can find already all the results. We have already prepared everything from you. You just need to unzip the folder and then you can check that everything is working correctly. So we are gonna run some steps all together, and then, I'm gonna take these results and show you the final results, so you can know. Today you can learn what to expect by this query by committee method. What we're gonna do is to start from our huge candidate pool of structures, select randomly for the moment a small data set, a training data set that will be used to create some initial machine learning model. And we also isolate a test data set that we will use at the end to compute the generalization error. This is pretty important, so always take a test data set that will not enter the training procedure, so that it's like a safe check that your workflow is correct. Then, after training our models, we will compute the disagreement over the candidate pool. This means that for each structure, we'll compute, we evaluate the energy and forces for our structures, and then evaluate how much our model disagree. And then we will enter this iterative loop. So we will pick up the bad guys of our dataset, of our candidates pool. So the structures which are hard to predict. So the structure where the disagreement is higher. We'll put the structures, put them in the training dataset, retrain the models, and go on and so forth. So the first thing to do is, of course, to train some initial models based on some random structure selected from the candidate pools. Here we have prepared a notebook with some minimal dependencies. Here in the my functions you can find some small simple functions that you can use to run this tutorial, and some hyperparameters. For example, in this case we are gonna train 4 models, a committee of 4 models, and we will select 50 structures in the test dataset and 20 as initial training set. You can run them. Just so the test could be, I mean, you need to perform some statistics on these sets. The larger they are for the test is better. In this case, 50 is a good balance, we say. For the initial training, I would say the smallest possible, because, okay, there are opinions. The more they are, the more expensive the workflow becomes. Yeah. I know. Yeah. The 20 here is really the ground zero, the force shot. And yeah, here, so we are starting with 20, but then as you can see, we are gonna add 10 new structure at each iteration. And for this tutorial, I mean, for this system, we have noticed that 15 iteration is more than enough, but I mean, this could depend a lot on your system or on your architecture. So, the first thing, as I said, is to generate the initial dataset. So from the huge pool, you just select 20 for training, 50 for test, and all the rest will remain in the red blob here on the candidates pool. So this is where we will pick structure and move them to the training dataset. So here the first thing to do is to actually train the first the models on this small dataset. This is done automatically by this cell. What is important to do is, let's go here, this is gonna happen in minute train, is that you need to train 4 different models and be sure that what you're gonna get out are different. They are actually uncorrelated models. So here we are creating 4 models with the same architecture, but the only difference is the seed random number, the generator for the seed for the random number generator. This means that when the 4 models will train, they fall down in different local minima, so that they will disagree on when predicting energy and forces on later on. So clear so far? So let's see. Okay, we have trained 4 different models. You can find them in this folder in trained models, and we can see that the error on energy and forces is okay for 20 structures, but we will do better by iterating this procedure later on. What we need to compute right now is the disagreement over the candidate pool, and here, oops. So the remaining structures in our candidate pool, we can compute for each structure how much our models disagree. And we can see that on average we have like a value of 60 MeV per angstrom. But we can see that we have some outliers, some structures which are the models that really disagree on them. They are the ones that are hard to predict, hard to learn. And these are the protagonists of actually this method, because right now what query by committee will do, will select, in this case we have decided the 10 worst predicted ones, put them in the training dataset, retrain, and so on and so forth. Yes, this is what this graph is trying to explain. So what we need to do is, okay, we just create a new folder with the same configuration file and so on. Okay, run QBC is what the query by committee will do. I'm not running it right now because it might take this win 15 minutes. So if you decide to use a different dataset, like the it takes more. So I'm gonna show you the result. You can try to run on your laptop to get a feeling of what's going on. I'm gonna explain you what is actually doing, so step by step. So what it needs is it takes the original models, not to train them from scratch. So we are gonna start from the pre-trained models. It needs the original trained dataset that will be augmented step by step. Also a test dataset, also always good to have an independent test dataset to check that everything is going well. And the candidates pool, these ones. And then we will ask to run for, in this case, we can set 15 iteration. 15 iteration to add, for example, 10 structure at each step, and we just need to provide how to train the models, which depends on the architecture, and so on. What you're gonna see is that, okay, we are gonna train a committee of 4 models. We are gonna run for 15 iterations, and we are gonna add 10 structure at each step. Here, some bookkeeping, we just copy the models, copy the dataset file, and then we actually enter, don't want to spoil, okay, we enter, yes? Yes. Enforces. Yeah, here it enters the loop. The first thing that it does is to evaluate the disagreement over the candidate pool. So it just will reproduce this plot here. That's it. Okay. Then it will select. Sorry, I think you're not seeing. Okay. It will select the 10 worst structures, the highest degree of disagreement. And here we can see that the average on the disagreement over the whole dataset is 64. On the selected one is higher. So the 2 curves that Christoph showed, these are the first 2 points of that plot. And then we put this structure in the training dataset and we retrain the models. This will take a while. Okay, in this case 28 seconds, depends on the architecture. And once we have retrained the models, we are done with 1 iteration. What happens is that we enter the second iteration. So we are gonna re-evaluate the disagreement, let's say, this plot, but with new models, retrained models. You select the worst one, you dominate train it, etc., and so on and so forth. At the end, here I've stopped after 15 iteration it should stop. Here, if you want to get the final results, you just need to run this bash script. It will unzip all the results in your folder and everything should work out of the box. So, as Christoph mentioned, it's really important to monitor how our query by committee procedure converges as we iterate. And what is going to happen, what you should see is a plot similar to the one sketched by Christoph, is that the red blob on the diagram above, so the candidate pool, the disagreement should go below and plateau after some iteration. The blue ones, the blue curves, are the selected ones, so the bad guys, the worst, the structures which has the worst disagreement. Also, this one should go down, but they will always be above above the average of. What do you mean? What people usually do when training, not with query by communities, say, okay, I want my model to be at least, I don't know, 50 milliV per angstrom, and I want my RMSE to be lower than that. We cannot do the same here because we don't know where to put the bar. We are gonna see later how these two things correlate, so you can play around with that. So here, if you see your these curves to plateau, means that you have extracted all information that you could from your dataset, or your model is, I mean, you should try with different architectures, because maybe your architecture is a bit limited and cannot do better, but let's suppose that it's fine. So here with 160 structures, we have extracted all information possible. A plateau. I will come to that point right now. Next plot, because what we have done at the beginning was to immediately isolate a test dataset to check later on, now, that our models are actually getting better. And here is where usually people say, I want at least, at most 50 MeV per angstrom. And oops, sorry. Yeah. Here you unzip the results. Yeah. No. In the zip file you get all the final results. What you see is by adding structures to the training dataset, your RMSE get lower. A safe value for models is usually 50 MeV per angstrom. Here we are getting lower, and we see that the RMSE gets lower even though we are not targeting this value to get lower. Does this answer? I mean, okay. So as Christoph mentioned, we are like targeting this quantity to get lower. RMSE get lower because the models agree more, but these quantities are two different things. Although they are correlated, and here, for example, we can see how, should not explode, we can see how the RMSE and the disagreement correlate at varying iterations. So at the beginning we have a large blob at high values, so high RMSE, high uncertainty. As we iterate, we see that both of them get lower, 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 lower. And then we get, so they both stay correlated, but they get both at lower values. So the more they agree, the more they are accurate. So far, any question? Okay. So, I'm gonna, this is the last part of this tutorial. One could ask, why have we done that so far? I mean, we have a super large candidate pool of structures. I know that I should not use all of them for training, but what if I just use, I don't know, 160 structures randomly selected, and just do it. It's easier. Why should I do all this procedure and so on? I mean, you can do it. This is what the third part of the tutorial is doing. It's just doing the same things as above, taking the original data set, then we select 160 structure for training, so the same number as we have reached here, just to have the same number, so to have a good comparison. And then we train on these randomly selected structures. What do you expect to get? Here, I'm not running. It will take 1 minute because I'm a bit late, but results is like double the error. So, and if you randomly select, as Mariana already mentioned and somebody else also mentioned in some talks, is that if randomly selecting, no, don't do that. It's wrong. You get bad results. Here you have with the same, with a data set of the same size, you have selected better. You have done a better choice of your structures, and this is pretty important. First, because it's cheaper. I mean, you get better results, and second, you can, I don't know, you have this data for PBE, and then you have a much smaller data set probably to, I don't know, hybrid functional and computing on fewer structures to save you weeks of work. And yeah, this was like what Christoph called regime 1, so training from labeled data, and now the second part that Shubham will guide you through is from regime 2 for unlabeled data.
Thanks, everyone. Okay. Hello, I'm Shubham. I'll be guiding you through the next tutorial, which is based on the regime 2 that Christoph already mentioned in his talk. So here, what we will do is we will tackle the eigencation through an exploratory simulation, and later we will make these models that just Ilya generated for Zundel better on this new system, which is eigencation. So you can open this second tutorial, which is to eigen.ipynb. It's in the same notebook folder. So you can see by running the first cell, you can see how eigencation looks like. It's a protonated water cluster, as Christoph mentioned, where hydronium is in the between and coordinated by 3 water molecules. Here, hydrogen atoms are asymmetrically coordinated between 3 water molecules. Now, in this tutorial, what we will do is we will use the trained model for Zundel that you just got from query by committee, and we will use to run a molecular dynamic simulation, run an exploratory simulation on this eigencation. Here, the Zundel machine learning potential have no idea about how eigencation looks like. It has never been trained on that system before at all. So here we will see how well it performs for the eigencation, and then we will analyze the committee disagreement on this eigencation, and afterwards we will improve these Zundel models on this eigencation by using the query by committee. But remember, here we don't have any labeled dataset. We are doing everything from scratch, so we have no information about eigen. We have only a structure of eigen that we start from. Can just run, just import some libraries and some functions. So the first task is to perform eigeninference, which is performing a molecular dynamic simulation at room temperature. Here we will do at room temperature. To do that, we have to go into eigeninference folder. You can find it in IPy example, which is just so in this folder you will find some bunch of files. Don't worry about them. You only need 2 files to perform the molecular dynamics with the committee. So all other files are just results that we have already provided you. So the first important file is the input file for the IPy. So IPy have already been introduced in other tutorials. So here we will use IPy to drive the molecular dynamics. We will connect IPy with the models that we have just generated to run the MD. So just to tell you, there are some important tags to remember to run a MD with a committee of models. So here you can see in the FF socket tags, there are 4 FF sockets. That means our IPy is connecting to the 4 models that we have just trained for the Zundel. So these are the addresses with which the maze potential will connect. And if you scroll down a little bit, you will see a weight factor, which is here just to compute an average of the forces that we get from each individual machine learning models. However, this is not the ideal way you should run molecular dynamics with the IPy. There is a predefined socket which you should use. So there is another file you can open, which is input FF committee. So there is a implemented socket which is FF committee. You should always use this FF committee socket because it will take care of computing the average by itself, and it computes the other uncertainties and other stuff in the loop by itself. So you don't need to worry about anything else. You just need to use this FF committee socket. And the other important thing that you need to for the pedagogical purposes, we will print out some other information. That's why we are using this other input file. And the other file you should provide is the initialization of the system, which is in the start.extended.xyz. This is just the extended.xyz file, which contains the initial position of the eigencation. So you can see it just by opening it. So this is just an initialization of eigencation to perform. Yes. And and then there is a run.sh file which just opens the IPy and connects it with the different machine learning potentials. So you can run the inference just by running the run.sh. Should work. I think there's Ilya. There should be. Now it should work. So what it does is it opens the 4 sockets, and then each individual machine learning potential that you have trained in the committee, they connect to this each individual sockets, and then IPy computes the mean of the forces that it gets from each individual sockets, and then runs the molecular dynamics. So you don't need to run this whole MD. You just need to unzip the. They are already there, but now they are hashtagged. So I would suggest you to just unzip the results that are already there, and visualize the trajectory that you have just generated. So this is the molecular dynamics that you have just performed with the Zundel models that have only been trained on the Zundel and have never seen the eigen at all. So you can see it's stable, but let's see how well the committee disagreements are on these structures. So here what we are doing is we are reading each individual forces that we got from the simulations and computing the committee disagreement that have been showed before. So in this plot what you see is the committee disagreement over the whole trajectory. In the blue one that we just performed on the eigen, and the black one is on the Zundel one that we have not performed, but we just ran in before. So we are just comparing a trajectory which is generated using the Zundel models on Zundel and on eigen just now. And here you can clearly see the committee disagreement on eigens are really large as compared to the Zundel, which you can really expect because these models have never seen eigen at all before. So now what we will do is we will improve this model just by putting some information about how eigen molecules look like. So what we will do is we will perform on the fly query by committee. It's exactly more or less the same loop. So right now what we have is we have some Zundel models and we will predict on this unlabeled candidate pool that we have just computed, and we will select the most uncertain structure based on the committee disagreement, and we will label them using the DFT. So we will compute the energy and forces for the structures which are highly uncertain, and then we will retrain the models, and we will do it again and again in the loop such that the uncertainty for this eigencation becomes better and better. So to do that we will need a ab initio DFT calculator. Here we are using FHIMs. So these calculations are a bit expensive, so I'm not running them right now, but you can of course run it. They work out of the box. They should work right perfectly fine, but they will take a little bit of time because ab initio calculations are a bit expensive. So it's exactly the same loop. You just add one thing in between, which is just computing, just labeling the data which are most uncertain. So right now we can just unzip the data which you get after performing this query by committee on the fly labeling loop, and then evaluate this refined model that we get after doing the whole procedure, and let's see how well it performs on the same trajectory that we have generated earlier and where we saw a very large committee disagreement. So coming to our last plot, so this is the plot that we will get at the end when we finish our query by committee and labeling on the fly. So on the y-axis, we again see the committee disagreement on the forces over the whole trajectory. It's the exact same trajectory that we have computed before, and the blue curve is exactly the same one which was before, where we saw the very high disagreement. But the green one is the one which we got just now after refining the model using query by committee and labeling the uncertain structure on the fly. So in this way we can refine our models, which are trained on one system, and can make them better on a similar looking another structure. And with this I finish my tutorial. If you have any question, please feel free to ask. Yeah.
Right. So I just wanted to add that with these notebooks, we have decided not to run explicitly many of the cells because they are just computationally very expensive. If you take this notebook as is, you can really run it. It will do everything that we promised, and it works. If you do it on the virtual machine, it should work as is, really without any modification. Just especially for the second part where we need to do these ab initio calculations, it will be very, very slow. So my recommendation would be to run this locally, but for that you need FHI aims to label these structures. You need to perform these calculations. Mariana explained that in the morning, that you can get a license for FHI aims. If you follow the instructions in the webpage, you can install and compile FHI aims, and then if you link it through the executable to your notebooks, you will be able to run everything. So take your time. This part will make your CPU sweat for sure. It will take like half an hour on full power, but you can get these exactly same results yourself actively.
So do you have questions?
Yeah, feel free to ask. You can even email us or open a query on the GitHub repo. We'll be happy to answer any questions. So,
okay.
Yes.
You have a question?
I think I did get something, but maybe it's a naive question, right?
Yeah.
But how did the active process using Eigen work in this case? I didn't get this. Where did this information come into the workflow? So I know that you taught us, but I didn't understand.
So we had a Zundel model, right? We computed from the first tutorial. At the end, we have a Zundel model which works perfectly for the Zundel model. We saw the RMSE on the test set going down, right? And now we want to use those models to learn this new system as well, because they look quite similar, right? Their atomic environments look quite similar. They both are water molecule.
So we have had, as Shubham just said, we have these models trained on the Zundel training set, right? And what we have asked for this model to do is nothing that a shameful, vulgar extrapolation, right? So we have forced the Zundel model to extrapolate on this other part of it's not the same configuration space, but on these other structures, and predict these energies, right? So we have we worked in the extrapolation regime, and we have used the active learning procedure, to select these structures to cover this part of the configuration space with training structures so the model gains predictive capabilities also for the eigen. Is that clear? Okay.
The only difference between the two regimes is that once you select the most uncertain structures, in the first case you know the DFT values and you can put them in the training immediately. In the second case, you have some structures, you know that the predictions are uncertain, but you don't know what is the true for energy and force, and this is where you need to label the data, so compute DFT, and then you can train and go on.
More questions? So, you learned everything about the active learning training. Okay, so I would like to thank you all for this tutorial, and also thank everyone that came from Hamburg and other parts of Germany. Mariana for helping with all the organization. It gave us quite a bit of work. But well, so both events finishing. Let's just thank everyone. Any final words, Mariana?
Gente, muito obrigada por estar aí, por ver os tutoriais também. Eu espero que vocês tenham pegado alguma coisa. Eu ainda vou fazer o setup daquele Slack channel. Eu vou coordenar com o James aí vocês vão receber o link aí proximamente. Se vocês tiverem alguma pergunta e tal, nos próximos meses, os tutoriais... Então, é melhor pelo Slack. E-mail, eu recebo 200 e-mails por dia. Você quer mandar, eu não vou ver. O Slack é melhor. Não, é melhor mesmo, porque daí todo mundo vê, entendeu? Aí tem mais gente que pode responder além de mim, porque meu inbox não tá bom. Tá doente. Então, e os tutoriais a gente vai deixar online também nos repositórios aí, que vocês têm o link e tudo, e é isso, vocês podem usar o quanto vocês quiserem, e qualquer coisa fala com a gente, espero que vocês tenham gostado, e é isso, gente, é um prazer estar aqui falando com vocês também, tá bom? Thank you so much. And please, big thanks to my group, the students, because they really prepared